Welcome back, everybody. Learning as a hobby here. I want to go over my chapter summary in Spivak for chapter 8. So I'm going to jump right into that. I have my notes written up here. Okay, so this is the last chapter in section 2 of the book. This is chapter 8, which is on the least upper bound property of the real numbers, which is the last sort of axiom that we need for the real numbers. There is also obviously there's a exercise set that I'm gonna work on after this video, but also there's an appendix and a solution and a exercise set for the appendix, which is on uniform continuity. And then I mentioned this before, but I also want to, after this chapter and the appendix, I want to go over Spivak's construction of the real numbers using Dedekind cuts, which is one of the appendices at the end of the book. And then we'll get into the part 3 of the book, which is where the differentiation and integration stuff starts. So starting here in chapter 8, let's just go through the summary. Now, as I always say at the beginning of these, there's more in the chapter than what my summary here talks about. My summaries, again, if you haven't seen my other videos, are just a skeleton of the chapter. You should read it yourself because there's plenty of other stuff in there that you might be interested in reading. But here's the sort of skeleton of the chapter. So he starts with a definition of a set A of real numbers being bounded above. So here, this is the definition. A set A of real numbers is said to be bounded above if there's a number x such that x is greater than or equal to a for every a in A. And such a number as x is called an upper bound for A. All right. And here I just have a note. If A is the set of all f of x, where x is between, not strictly, but is let me start over. A is the set of all f of x such that a is less than or equal to x less than or equal to b, then the function f is bounded above if and only if the set A is bounded above. So he's just making a distinction between a set of real numbers being bounded above and the concept that we talked about in the previous chapter, chapter 7, of a function being bounded above or bounded below. So that's the connection. Okay, here we have a definition of a least upper bound. So a number x is a least upper bound of A if there's two things. X has to be an upper bound of A, and 2, if y is an upper bound for A, then x is less than or equal to y. So that's what they mean by least upper bound. Okay, it's the smallest upper bound for the set A. Right, another note here. In fact, x in the definition here, he says is a least upper bound, but in fact, least upper bounds are unique. In fact, x is the least upper bound of A, since if x and y are least upper bounds for A, then x is less than or equal to y, and y is less than or equal to x from the definition, which implies that x has to equal y. So if a set has a least upper bound, there's only one least upper bound. All right. And just some terminology here. If x is the least upper bound for a set A, then it is sometimes called the supremum of A. And in different books, actually, in a lot of books, they use these terms interchangeably. These are the abbreviations. X would be written like this: LUB of A, which is read least upper bound, or sup A, which means supremum of A. They mean the same thing. That's just some shorthand notation, so you don't have to, always write out least upper bound or supremum, because it can be kind of annoying to do that. Okay, some more definitions before we get to, oops, let me just make sure I didn't turn the volume off. Okay, just some more definitions before we get to proving the theorems from the last chapter. A set A of real numbers is bounded below. We already talked about what bounded above meant. So a set of real numbers now we're defining to be bounded below if there's some number x such that x is less than or equal to A for every A in A. Right, such a number is called a lower bound for A. And using that idea, we can define what we mean by a greatest lower bound of a set. So a set of real numbers, a number x is the greatest lower bound of A if, again, there's two conditions. X has to be a lower bound of A, and if y is a lower bound of A, then x is greater than or equal to y. All right, so again, if a set has a greatest lower bound, it's unique. There's only one greatest lower bound for a similar reason for least upper bound. Okay, some terminology. If X is the greatest lower bound of a set A, we call it the infimum of A. And here are some abbreviations for that. So if X is the infimum of the set A, sometimes they'll write inf A, that stands for infimum A, or GLBA for greatest lower bound of A. Okay, and then here's our final axiom that we need for the real numbers. This is called the least upper bound property. If A is a set of real numbers, A not in the empty set, and A is bounded above, then A has a least upper bound. So this is an important property that the real numbers possess. Now we're not really at this point, we're not really sure that there is even such a set, but we'll construct it and show that the real numbers actually do exist, and they're defined, like I said, in an appendix at the end. So there is a set that we call the real numbers that has this property. Okay, some notes here. If A is empty, then every real number is an upper bound for A. And therefore, A equaling the empty set has no least upper bound. So that's why we need that condition in the axiom there, right? And then also, this may seem like a very intuitive idea, but there are sets that don't have this property. For example, the rational numbers. So obviously, this property doesn't hold for the rationals because, for example, the set A equal to all rational numbers X that have square less than 2, that has no least upper bound in Q. Q is the set of rational numbers, if you remember. That set has no least upper bound because while it is bounded above, for example, it's bounded above by 2, the least upper bound in the real numbers would be the square root of 2, but the square root of 2 is not a rational number. Therefore, there is no least upper bound in the set Q. So not every set has the least upper bound property. That's one of the things that makes the real number special. All right, and it's also one of the reasons why we use the real numbers for calculus. So, okay, theorem 7.1 from the last chapter. Remember, we said the heading of the last chapter was 3 hard theorems, and we said we're holding off on proving those 3 hard theorems until this chapter, and that's what we're going to do now. So theorem 7.1 was the first theorem in chapter 7. So I'll just restate it here. If f is continuous on the closed interval from a to b, and f of a is less than 0 is less than f of b, then there's some number x in the closed interval from a to b such that f of x equals 0. So now we have the machinery. I can't, for some reason I can't talk today. I don't know what's going on. We have the machinery now with the least upper bound property that we can use to prove this theorem. So let's just go through it. So let A be defined to be the set of all x in the closed interval from A to B, such that f of alpha is less than 0 for all for all a less than or equal to alpha less than or equal to x. Okay, then A is an element of the set A, obviously, because just going back up here, we said f of A is less than 0. So that's A is in the set. So that implies that A is not empty. So also f of B is greater than 0. Therefore, A is bounded above by B. Therefore, A has a least upper bound just by the least upper bound property of the real numbers, okay? Which I'm calling here X squiggle, I guess, or X tilde. Either f of X tilde is less than 0, f of X tilde is greater than 0, or the only other possibility is f of X tilde is equal to 0. Assume for the sake of contradiction that f of X tilde, again, which is the least upper bound for that set A, is not 0. Okay, and then I'll consider 2 cases. I just have to show basically that under that assumption, one of these two either this or this has to be true, but that'll lead to contradictions. So that's what I'm doing here. All right, case 1, assume that f of X tilde is less than 0. Then f is continuous on the closed interval from A to B, implies that there's a delta greater than 0, such that for any 0 less than absolute value x minus x tilde less than delta implies f of x is less than 0. Then take x star in the interval from x tilde to x tilde plus delta, then f of x tilde is less than 0, and x tilde, notice, is less than x star, which contradicts that x tilde is an upper bound for a. So that's a contradiction. Right, so let's try, maybe it's case 2 that works. So case 2 would be f of x tilde is greater than 0. Then there's a delta greater than 0, such that 0 less than absolute value x minus x tilde less than delta implies f of x, implies f of x is greater than 0, sorry. Then x star, if you take x star in the interval from x tilde minus delta, comma x tilde, the open interval, then f of x star is greater than 0, which contradicts that x tilde is equal to the supremum of a. Therefore, f of x tilde has to be 0, because case 1 and case 2 both lead to contradictions. The only other option is that f of x tilde is equal to 0, so that has to be the case. And that proves the theorem. So this first theorem here from chapter 7 is now proven. And if you recall, we actually used this theorem to prove a bunch of other theorems in chapter 7. So now all of those are established, without any problems. Okay, and then there's some supplementary results that we need to establish before we look at the other two theorems from chapter 7. So here they are. Theorem 1 says, this is theorem 1 from chapter 8. So if f is continuous at a, then there is a number delta greater than 0, such that f is bounded above on the interval from a minus delta to a plus delta. This is the open interval. So here's the proof. It just follows from continuity. So here's the proof. Let f be continuous at a, then for example, we could choose epsilon equal to a half. There's nothing special about a half. You could choose any other positive value if you like. There exists a delta greater than 0, such that absolute value f of x minus f of a less than 1/2, when 0 less than absolute value x minus a less than delta. That's from the property of continuity. Then for any x in the open interval from a minus delta to a plus delta, minus 1/2 less than f of x minus f of a less than 1/2. That's just the compound inequality that's equivalent to the absolute value inequality that we had on the previous line. All right, and then you can add f of a to all three sides. So f of a minus 1/2 less than f of x less than f of a plus 1/2. Therefore, f of a plus 1/2 is an upper bound for f on the open interval from a minus delta to a plus delta. All right, and then he says here in the book, after that theorem, actually there's a bunch of other results that we'd like to establish, but the proofs are very similar to the one we just did. So he skips them in the book. He says you should do them. I didn't do all of them just because the proofs are virtually identical, just with some slight alterations. But I did prove one of them just so you could see how it's done, and then you could try it on your own if you want to. But here's the note. Similar arguments to the one above allow us to conclude that f is bounded below on the open interval from a minus delta to a plus delta, and finally that f is bounded on an open interval containing a. More significantly, if limit x goes to a from above, so this is the one-sided limit of f of x equals f of a, then f is bounded on the interval from a to a plus delta. Here we're including the lower endpoint a, but the upper endpoint is excluded. You can think of this as sort of like the we really haven't talked about topology, but this is sort of like, from the subspace topology on R for the interval a, b. But anyway, it'll be true on this interval. For some delta greater than 0 and limit x goes to a from below, f of x equals f of a implies f is bounded on the interval from a minus delta to a, including the upper bound a, for some delta greater than 0, as you should prove. So here, like I said, actually didn't prove all of them. I proved one of the one-sided cases just because that one is different than theorem 1 that we showed up above. So, but you could do the other cases in a very similar way. So I'll if you want to do that, you can try that. I just didn't feel like writing the same proof over a bunch of times. Okay, so here's theorem, what I'm calling theorem star. If limit x goes to a from above, f of x equals f of a, then there's a delta greater than 0 such that f is bounded on the interval from a to a plus delta, including a but not including a plus delta. So here's the proof. It just, again, follows from the one-sided continuity here. Limit x approaches a from above of f of x equals f of a implies for epsilon equals 1/2, there's a delta greater than 0 such that absolute value f of x minus f of a less than 1/2, when 0 less than x minus a less than delta. I don't need the absolute value there because it's a one-sided limit. Then if x is an element of the set a to a plus delta, negative 1/2 less than f of x minus f of a is less than 1/2. And if you add f of a to all three sides, you get f of a less than negative 1/2. I'm sorry, you get f of a minus 1/2 less than f of x, less than f of a plus 1/2. Therefore, f is bounded on, bounded means bounded above and below at the same time. So f is bounded on the interval from a to a plus delta. Okay, so, and like I said, the other cases are similar, so you can try those if you want to. But I skipped it just because I just didn't feel like writing the same proof a bunch of times. Okay, so now we're ready to prove theorem 7.2 from chapter 7, which, if you recall, is this theorem here. If f is continuous on the closed interval from a to b, then f is bounded on the closed interval from a to b. Okay, bounded means bounded above and below. So here's the proof. Again, it follows from the least upper bound property. So let's start by defining the set A to be the set of all x in the closed interval from a to b, for which f is bounded on the closed interval from a to x. Right? Since x is less than or equal to b for any x in a, a is bounded above, and also it's not empty because a is in that set as well. I probably should have wrote that. Then x tilde equals sup a exists. Since f is continuous at x tilde, there exists delta greater than 0, such that f is bounded on the interval from x minus delta to x tilde minus delta to x tilde plus delta. Furthermore, f is bounded on the closed interval from a to x tilde minus delta. Since x tilde is sup a, therefore f is bounded on the entire interval from a, from a to x tilde plus delta. So we get a wider interval here by the fact that the set above is has at least upper bound. Then for any x in the interval from x tilde to x tilde plus delta, f is bounded on that interval. So in other words, absolute value f of x less than or equal to n less than infinity for some n in the interval from 0 to infinity, and x tilde is less than x, which contradicts that x tilde is the supremum of a. Therefore, f has to be bounded on the interval from a to b, including a, but not necessarily including b. So it has to be bounded at least on that interval. However, f is continuous at b implies that there's a delta prime greater than 0, such that f is continuous on the interval from b minus delta prime to b, excluding the lower endpoint, but including the upper endpoint. Therefore, f is continuous on the union of those two intervals, which, if you notice, it unions to give you the entire interval from a to b. So now 7.2 is established, and we go on to 7.3. And once we've done all these, then all the theorems that we proved in chapter 7 follow from them. So okay, let me just reread theorem 7.3 in case you've forgotten it. If f is continuous on the closed interval from a to b, then there's a number y in the closed interval from a to b such that f of y is greater than or equal to f of x for all x in the closed interval from a to b. Okay, let's go on to the proof. He says in the before this theorem also that the proof for this also, in addition to the needing the least upper bound property, it also requires that you sort of be clever enough to figure out a trick, which I'll explain when we get to it in the proof. So since f is continuous on the closed interval from a to b, f is bounded above on the closed interval from a to b. That follows from the previous theorem, right? Therefore, b equals the set of all y equals f of x for x in the closed interval from a to b is bounded above. So b has a least upper bound, which I'll call beta. So beta is sup b. assume beta is not in the set B, then here's the trick. That's why I have it labeled with a star here. This is the trick that you need. Define the function g of x equal 1 over beta minus f of x. Then g is continuous on the closed interval from a to b, since beta minus f of x is never 0, under our assumption that beta is not in the set B. For any x in the closed interval from a to b. Then for any epsilon greater than 0, there is an x in the closed interval from a to b such that beta minus f of x is less than epsilon, since beta equals supremum of b. However, this implies that g of x equals 1 over beta minus f of x is greater than 1 over epsilon. All you do is just take the reciprocal of the inequality. Just be careful when you take reciprocals of inequalities, you have to switch the direction of the inequality, so that this follows from this inequality just by taking the reciprocal. Okay, so that inequality holds for any epsilon greater than 0, which contradicts the fact that G must be bounded on the closed interval from A to B by the theorem that we just proved before. So theorem 7.2. Okay, there we go. That's the 3 hard theorems from chapter 7. Now we have them. There's a couple more things that he does in section 8 that are also needed, that are important for the real numbers, which is what's called the Archimedean property. But let's go through the theorems here. This is theorem 2 from chapter 8. And this theorem says that the natural numbers is not bounded above. So here's the proof. Again, it uses the least upper bound property. So assume, for the sake of contradiction, that n, if you remember, that fancy n means a set of natural numbers, just to remind you, in case you've forgotten. Assume that n is bounded above, then the fact that n is a subset of the real numbers, and n obviously is not empty, because, for example, it contains the number 1, implies n has a least upper bound x. Then for any n in the natural numbers, that would mean that n is less than or equal to x, right? If x is the least upper bound, then all integers have to be less than or equal to that number. Also, n in n implies that n plus 1 is n. Remember, the natural numbers are closed under the successor operation, right? And n plus 1 would also have to be less than or equal to x, which implies that n is less than or equal to x minus 1. Since n was arbitrary, n has to be less than or equal to x minus 1 for all natural numbers n, and this contradicts the fact that x was the supremum of the natural numbers. Therefore, the natural numbers is not bounded above. Okay, so we already knew that the natural numbers were infinite, but this establishes it using the least upper bound property. Okay, I think this is the last thing, in chapter 8. So theorem 3, for any epsilon greater than 0, there's a natural number n with 1 over n less than epsilon. And here's the proof. Assume there is an epsilon greater than 0, such that for all natural numbers n, 1 over n is greater than or equal to epsilon. So in other words, I'm doing this by contradiction, so I'm just assuming the negation of the statement above. Then n is less than or equal to 1 over epsilon for all n in n, but that contradicts the theorem that we just proved above, that there is no upper bound for the natural numbers. All right, so therefore it has to be true. This is sometimes called the Archimedean property of the real numbers, and it's a very useful property, which I'm sure we'll be using later on down the line. So let me just double check that that's it. Yeah, I think that's all. That's everything from chapter 8. So let me stop the screen share. Okay, so we're almost done with part 2, guys. I still have to do the exercises from chapter 8, and then, like I said, there's a small appendix on to chapter 8. I mean, on uniform continuity, with a small exercise set for that as well. And then also after that, I want to do the appendix on constructing the real numbers using Dedekind cuts, and then finally we'll get to differentiation and integration in Spivak. So be patient. We're almost there. And then also, like I mentioned in previous videos too, I also want to get through the foundational stuff in Tao's book on analysis. So there's a few chapters in there that I want to get through also. So I'm going to end the video here, guys. Keep an eye out for the chapter 8 exercises, which should be coming out as soon as I get them done. and then we'll look at that appendix after that. So I'll see you guys in the next one. Until that time, keep learning, everybody. Oh, I should also say, if you like the content, just to remind you, you can hit the subscribe button, hit the bell icon, hit like the video, etc., etc. Take a look at the Patreon page, and I'll see you guys in the next one.